Hi. So this is the next thing, which is looking at trigonometric, undefined trig equations. It's just another type of question. And this one says trig equations can be used to determine values, but also can be utilized to find where a function is, in this case, undefined. Recall that a function is undefined when the denominator is equal to 0. And then it gives us this trig expression. Determine where the trig expression tan a half theta minus pi over 2 is undefined. Okay, so then I did a solution to it, which I'll pull up. And I need a solution to it, which is there. Yeah. Cool. All right. So this is 509 video little 6, and I'll do this thing where I'm using this highlighter. So things that I'm not comfortable about is undefined, and it says denominator, and oh man, can I remember? Numerator's on top, denominator's on the bottom. So I've got to jog my memory a bit. It says the undefined trig equation, determine when the trig expression so-and-so is undefined. So I'll put down here, remember undefined means that in a fraction, the denominator is 0. So that's like 7 over 0 or 12 over 0. My day would say it goes to infinity. Now we say it's undefined. Then you can see I started going off on a wrong bit, because what I said to myself was, oh, that means that tan a half theta minus pi over 2 equals 0, because there was 0 in my mind. And it doesn't. It actually means it should be infinity, or as close as you can to it. It means that the denominator equals 0. So I had to stop and I had to go, oh, hold on. If I remember that tan theta, I'm going to pull this up a bit. If I remember that tan theta is equal to opposite over adjacent, which is opposite over hypotenuse over adjacent over hypotenuse, then tan theta equals sine theta plus cosine theta. So I say, okay, tan whatever it is equal to sine whatever it is over cosine whatever it is. And for an undefined function, it's this bit at the bottom that has to be 0. The bit at the top can be whatever it likes, but it's this bit at the bottom has to be 0 to be undefined. So then I say, remembering that undefined means that the bit on the bottom equals 0. So then I can say that cosine over half x minus pi over 2 equals 0. That's the correct statement. So they're making you, they're deliberately making you do this extra step. They're trying to catch to see how many people put down tan so-and-so equals 0, like I was going to do. And sometimes you'll walk in that direction and then you'll catch yourself. That's just the way it goes. You're doing really quite complicated things here. And then we say, okay, well, visualize. So I say, well, here's my unit circle. And I want the value when the cosine is equal to 0. And the cosine is equal to 0 when we have, so let's just remind ourselves of a bit here. Whenever I start hesitating, I know I need to slow down and think a bit. So there's a generic angle. This is my angle in the first quadrant. Here's my hypotenuse, and for the unit vector that equals 1. And then here's my x and here's my y. And my x is my cosine. Cosine of that angle equals x over 1. It's the adjacent over the hypotenuse. So I want to know when that x, what angle does that x go to 0? And it goes to 0 when you're vertically up, and it goes to 0 when you're vertically down. It goes to 0 on that line there. I know on that line there, cosine of theta equals 0, and I know cosine of theta equals 0 because the x has gone to 0. And then the question is, what angle is it? So I'm drawing my angles in now, and what I get is, well, it's going to be, if you think about it, it's going to be 90 and 270. So I say cos to the minus 1 of 0, the angle at which you get a cosine of 0 is equal to 90. Is equal to 9. You can't see that, can you? Is equal to 90, and it's equal to 270 just from that observation. And we like to put this in radians, so it's pi over 2 and 3 pi over 2 radians. And then, okay, a lot of people will put that down as the answer. I bet it's on the multiple choice. But then you got to realize that, oh, hold on, let's look back at our equation. Our equation is not theta, tan theta, it's tan a half theta minus pi over 2. So then I've got to come back down here and I've got to say, okay, so then I know that, let's call this expression here another Greek letter phi. This a half theta minus pi over 2, let's call it phi. We just worked out that phi is equal to 90 and 270. But also phi was equal to pi over 2 and 3 pi over 2. But we want to know about little theta. So we say, well, a half theta minus pi over 2 equals my first answer, which is pi over 2. Let's rearrange that. A half theta is equal to pi over 2. That negative goes to positive. 2 halves make a whole. So a half theta makes pi. So theta makes 2 pi. And what we're saying here is, well, okay, in that case then a half theta minus pi over 2 is equal to 3 over 2 pi. So a half theta is equal to 3 over 2 pi plus a half, that's just pi over 2, which equals 4 pi over 2. 2's dividing, multiplies on the other side. Theta is equal to 4 pi. So there's my answers again. And again, let's remind ourselves, they have not asked us, and we've not said, well, this repeats well, this is a cosine, so every n 2 pi's, you know, the next time we go around the circle, that's not come up. And I'm just thinking about something. And they didn't do that this time, you know, because they've practiced it and now they're not practicing it, you know, but they could have asked us to do that. And then the other thing I want to say to you is, you know, so how much of this am I writing down because I'm trying to explain it to you, and how much of this am I writing down because I need to write it down? And I'd say this box, remember, undefined means that in the fraction denominators, I probably won't write that down. I'd probably put down a little bit of it like, oh, 7 over 0 minus, or 12 over theta. I'd probably put down something about thinking about it, and then remember that tan equals that. I wouldn't write all that down, but I would put down tan theta equals sine theta over cos theta. And why would I put those down? Because it's reminding me. It's not just all in my head, it's on the paper as well. But all this other stuff I'd write down, you know, for a couple of reasons. One is that the more I write down, the less I have to hold in my head. So my head is free to think rather than trying to juggle things. And the second thing is for checking my work. I can just look at this and I can read what I put down. So as I've gone from being a student to being a teacher, I found that I have to get questions right the first time, you know, in a class. And the way I do that is I write more down. And I tell my students, write more down than you are. One last little thing under, well, I can show it on the bit. So if I go from here and I go back to here, what it then does, basically got the same solution, and then it sort of says, well, look, if you look at a tan function, when does the tangent become undefined? It becomes undefined when you divide by 0. That means it gets bigger and bigger and bigger. So it's pointing out that, oh, look, you're asymptotically approaching infinity at 2 pi, and you're asymptotically approaching infinity at 4 pi. So it's justifying the answers by the graph as well. And then this final little bit is interesting. It goes, many of the key features of trig functions can be solved using trigonometric equations, including zeros. So what they could do, they're kind of telling you now, is what we could do is we could ask you, oh, find this function when it equals 0, or find the y-intercept of this, or find the vertical asymptotes. To find the 0 of a function, set the equation equal to 0 and solve it. That's easy enough. To solve for the y-intercept, replace any x values with 0, because at 0x, you're crossing, you're getting the y-intercept. And then solve. To find where the function has a vertical asymptote, determine where it is undefined, where the denominator of the function is equal to 0. So what they're saying there is, they're saying, look, you can play with these equations like you would do in algebra. They're not magic. None of this is magic. It's just got, there must be 10 bits that you need to have in your toolbox to solve this problem. It's not one thing. It's 10 previous things that you're relying upon to do this one thing. So, and if any one of those is missing, then you're struggling. And that's what happens. So what I say to students is, by doing more homework, what you do is you're forever going back and you're digging out of the toolbox the tools that you need. And you're getting better and better at using them. And you realize, oh, this is really important. It keeps coming up. This is really important. So just stick there with it. But I'm not seeing your work, but my sense is when I grade people's papers, I see a piece of paper with a few numbers on it and the wrong answer very often, because they're trying to do it all in their head and it's not working for them. And I see, well, I've learned the more I write down, the better chance I have of getting this right. Because it's part of me. I'm interacting with the page all the time. Cool. Okay. See you later.